zoom in the formulas here that we have over here, that gives us an expression. So for example, we'll still have the loop momentum appearing in here. But we have a substitution formula for the various pairs. We plug those in, and then we basically are left with a little bit of algebra to do. I'm not going to do that for you. But again, I encourage you to work that out yourselves. And what we find is the following formula when all the dust is settled. And I think at this point most of you will recognize what that formula is. It's exactly the tree-level formula that you would get. And up to a sign here, which I'm not sure I got right. It turns out, if you look at, if you think back actually to the easy two-mass box formula we wrote down, there was a denominator, which was essentially ft minus m1 squared, m3 squared, or there was m2 squared and 4 squared, but rotate the box. And here, of course, we're taking a one-mass box, so m3 is actually 0, so the denominator is ft. Well, what is ft in this box? It's, of course, f34 times f45. So this is exactly the denominator of that box, of that interval. That isn't at all an accident. That turns out to be, in the NHV case, the kind of general pattern. And in fact, even though I haven't told you that explicitly, secretly we've been not only doing this computation in QCD, but also in n=4 supersymmetry. For this particular box, you cannot have the fermion running here because it would violate helicity. Remember that helicity conservation for the fermions says that we have to have a plus and a minus at opposite ends of the fermion line. So the fermion contribution will actually vanish, and in fact, with charged scalars, there's no helicity, but if you use the charge of the scalar, the same argumentation applies. So for this particular contribution, in this particular amplitude, QCD and n=4 supersymmetry have the same contribution, and so we calculated it in n=4 supersymmetry as well, and this is, in fact, the general pattern, this kind of denominator of the box times the three amplitudes for the NHV helicity, which is, of course, very special to the Park-Taylor helicity pattern. So, as I should have expected, there won't be time to do the triangles in any great detail, but there was a question earlier, and I'll take just a few minutes to outline how things go. Yes, sure. So the question is the coefficient always in NHV3? I think that's the answer. So that's special it's special to this NHV configuration. And in QCD, it's not a general proof. There's other contributions. Because, for example, there will be triangles and their coefficients are not exactly NHV trees. But in n=4 supersymmetry, this is a general pattern, not just at the 5-point, but at the 6-point, as long as we're looking at the Park-Taylor configuration. So as long as there's two negative helicities in the remaining plus yes, then you in fact get a factor. All the spinorial factors in a sense are exactly the three amplitudes, and that's one of the things that's very special about the n=4 theory. There is no second solution because it's essentially going to it's essentially eaten up by the fact that some of them vanish. So there's two solutions, but sometimes the coefficients, the product of amplitudes in a given solution can vanish, and that's essentially what happened over here. The one half is always there, but it can be, so you're supposed to sum in a sense over both global poles, but it can be that the residue in one case is 0, and that's what's happening over here. So in the minus 5 minutes that I have, I'm just going to draw one picture and tell you in words what happens in the case of the triangle. So let's think a little bit about the two-mass triangle. So here we have a triple cut, and the way I'm going to explain it here is not exactly the way in the literature as that the paper, particularly Darren Ford's paper, which is from 2007, which is the one that first worked out how to do these coefficients, was before some more modern understanding of what to do with delta functions, but I think it is equivalent to, ultimately it's equivalent to what he did. So we now have a 3-torus that encircles the triple cut. So basically the way we would proceed in derivation is you write down general parameterizations the loop momentum in terms of, for example, spinorial quantity. And we would do the integral around the C3, that is essentially imposing the triple cut. Of course, we have four components, so there's one remaining degree of freedom. Let's call it T, the notation that Darren used. Remember that there's a Jacobian, I'm going to erase now, but there's a Jacobian in general that arises. That's the derivative of the polynomial denominator. And in this case, the Jacobian has the form of some constant. Constant in the sense of it doesn't depend on the loop momentum, it depends only on the external kinematics divided by T. And that allows us, instead of leaving T to be determined by its original contour, which is somewhere, it's determined by the real contours of the original loop momentum. So it would have naively some contour if we were trying to do the integral, but we're not trying to do the integral. We're free again to replace that contour with a little circle about one of the two poles, which are at 0 and infinity. It turns out it's more convenient to think about the pole at infinity, at least to make a link with what Darren was doing, because if we have some numerator, so now in general, what's going to happen? We have a parameterization of L that depends on T. So when we plug that into the tree amplitudes, we're going to have each of these amplitudes is going to be a function of T. So this thing is now going to be a function of T. And it turns out that what we essentially need to do is a contour integral dt over T of this function of T. Now, this function of T still has boxes in it, but those boxes we know have solutions somewhere out in the complex plane. So a typical box is going to have two solutions, and there's some location somewhere out in the complex plane. And you can solve for them explicitly if you know the list of boxes. So what we want to do is actually just isolate, for example, the pole at infinity, and that's easier to do because in fact the form table typically have a sheet for power counting. The thing that we're looking for is ultimately a constant term as t goes to infinity. So as t goes to infinity, these boxes will go away because they're scaling like 1 over t, and the residue that's left at infinity is going to give us the coefficients of the triangle. Of course, in general, t or is 1 over t, so the triangle, in general, if you ignore the contributions of the boxes, has terms that go anywhere from t to the minus 3 t cubed, and the thing that we're interested in pulling out is the t to the 0 contribution. So the way you can do that is to define an operation which Darren called inf, which says take the polynomial term as t goes to infinity. And then at the end of the day, what you're going to want to take is the t to the 0 term, which is the residue of the pole at infinity. So again, conceptually, it's the sources of the residues and the sources of the contours are a little bit different from the boxes, but the way things work out is the same. We replace some of the contours to get a triple cut. It turns out that offers us the possibility of changing another contour to fully localize the integral. And as a contour integral, we can simply choose, for example, to do it around t equals infinity. Now, let me just say a couple more words about what happens in the numerical approach. So in the numerical approach, again, you could imagine just doing this contour integral, let's say, around 0 numerically. That's not numerically stable because you don't know really. I mean, you could compute and you could make the contour small enough, but in general there may be oscillations that are due to the presence of these other poles, and it's harder to get them under control. So in a numerical approach, it's actually useful to combine this, if you like, the contour-based approach with a subtraction that's one of the ingredients in the OPT approach that Jeff Paolo has been talking about. So the kind of thing you would do is you would take this product and you would subtract the boxes, which you already know because you computed them before. This object is now going to have only a finite Lorentz expansion, as you, let's say, around any fixed circle. You could take one conveniently at t equals 1, for example. And so this thing you can actually apply, you can do the contour integral by doing a discrete Fourier sum, basically. And that's the way things are done in Black Hat. I realize that may sound a little bit sketchy to many people here, but I hope it at least gives you a flavor of how things work for other integrals.
By LMU Munich.
Hey, good morning, everybody. And I thank the organizer for this nice event, and I hope that we all will make it really as a enthusiastic occasion to discuss about the rapid development that we have been witnessing in the last, let's say, 6-7 years, and about the new calculation techniques for computing scattering amplitude, but also about a new understanding probably of the properties of quantum field theories. So I have titled my lecture Basic Structure of Scattering Amplitude because at the beginning of this so for the first 3 hours, I'd like to settle down the notation, hopefully common notation among the 4 speakers of this school, and try to get the contact between the notation that you might find in a usual textbook and a more compact notation that we will be using. And for the rest, for the second 3 hours, I will discuss more about advanced topics. So today we stay at sea level, and then we move one loop higher day by day. So just one loop per day, like the reactor keeps the doctor away. So the reference material that I'm using for this introductory lecture is listed here, and I try to alternate blackboard talk calculation, mainly QED based, with some more lengthy formulas for TCD that I will show on the slide. So you don't need to take notes about the slide because they are available to you eventually. Just take notes of what will be on the blackboard. Okay, if there are questions anytime, you can just interrupt me. So when we think of particle scattering at hadron collider, for instance, we start with and switch. Incoming proton, then we have some of its components colliding with another particle. Okay. The collision is usually kind of quite involved process to describe completely. Some basic representation can be sketched in this way. Really the beam in the accelerator machine, the observed particle, we could divide the whole process in technically 4 phases. There is an initial part ruled by the particle distribution function, which describes the probability that some particle can generate what is the Hall scattering. Then there is a phase where particle shower, and then there is a last phase, the ionization and decay, where particles recombine together to be observed on our experimental site. And this dashed line here are a very sketchy parameterization of our ignorance. Okay, and then we can describe the evolution, let's say, of the particle production and according to the energy involved. Okay, and what I will be concentrating on for the rest of my lectures and probably also for the rest of the workshop will be something related to this phase, okay, in particular to describe the interaction, the big interaction among the partonic element of the collision. So the basic quantity that we all learned during our quantum field theory course that describe the probability of an event to take place is the cross-section, okay? And this formula should be known to all of you. So the cross-section contains 3 types of building blocks, namely a flux factor, then an integration over the free space, and what we have here is the amplitude squared summed over of the spin and average over spin of the incoming particle. So this is the first place where the scattering amplitude enters the game of quantum field theory. And in particular, scattering amplitude and the picture of Feynman remembers that at the beginning of the talk. So scattering amplitude can be obtained by sum over diagram, so over Feynman graph of incoming or diagram involving incoming particle, okay, going to other process of particle production from 1 to n, so 2 incoming particle and particle production. And the integration of the free space happens to involve only the momentum of the produced particle. What actually we need there in the cross-section is not the scattering amplitude by itself, but as I said, we need the square of the scattering amplitude. And we can compute the square of the scattering amplitude simply by taking the complex conjugation of these diagram and summing of all possible gas. This is a word that will become more and more used along this lecture, not only in my session but also in my colleagues. And the gas graphs are obtained by taking the complex connectivity of the diagram that I'm showing here on the top. Okay, and by joining the external particle. Okay, so this is the building block that we need in order to compute the amplitude square. And I will leave there on the slide a list of Feynman rules, okay, which we can use to compute the amplitude square sum of the spin of the particles involved in scattering. Let's see this example. What I mean, let's describe, for instance, the glass minus, so the glass minus in QCT. The Feynman diagram of this process is just one. So an electron, the photon exchange, and a muon there produced. This is Q, the transfer momentum, and we define the Mandelstam invariance S, like the momentum of the electron plus the positron, square in T, which is electron minus mu square, equivalently the positron minus the mu, and then u. And according to the rules that are written on the slide, we can get the sum of the spin of the opposite exactly by taking the complex corrugated Feynman diagram and joining the external line and paying attention to the terminal line flow. Okay. For this graphical representation, we would write here the 4 pi alpha over s squared, where s technically is q squared. And then we have to compute these from the top trace. This trace is based on the external dynamic line and the based on the internal, which we could write like this. Electron times the trace until and we are just proceed here to the electron. We have for the position of the muon and of the muon and of the momentum of the electron. So technically what we are doing in summing of electricity or the equalization of the spin of the final state, we are joining this line here, this dynamic line, and using the completeness relation, which relates exactly the spinous wave function to the numerator of the Feynman dynamic probability. Okay, and with regular standard techniques that we should learn at the theory course, we are able to compute the stages among the magnetics and to find the result, which looks like 8 times 4 pi alpha squared. And then here, there is a term which involves the square of the Mandelstam invariant plus other terms which involve the mass of the particle involved, okay? And which for the moment I'm not interested in, so we will forget. So, these should be another straightforward calculation according regular standard techniques, and we are able to compute for the square amplitude for this process. I like you to remember this result, particularly so the massless term result, because we will meet in the future in the next hour. Yes, please. also technically